Okay, so for the change of topic, we're going to finally start with nonlinear equations. So you can forget about everything. Okay, so the goal that when I started working with this some time ago was motivated by general relativity. So can you determine the topology and the metric of space-time by making observations near the Earth or in a space station or somewhere like that. So this is a picture of a wormhole, gravitational wormhole that has not been found yet although there is a possibility predicted by the general theory of relativity. So wormhole is a shortcut in space-time. So here is an image of space-time. You can go to the future through a wormhole. Okay, so this is science fiction at the moment, but electromagnetic wormholes that act like a wormhole for electromagnetic waves, this has been done in laboratories, not just theoretically. And this is how it looks like the end of a wormhole over a chessboard under the blue sky. This was done work with Alan Greenleaf, Jaroslav Kurilev, and Matti Lassas. Okay, so the point of this is to show that for nonlinear equations, the inverse problem is easier. Suppose you have this equation, the linear equation here. We don't know how to deal with the case that the sound speed depends on time for the inverse problem, the same inverse problem that we considered. However, because of you saw there a new wave appearing because of the interaction of several waves. New waves appear because of nonlinearity. This is non-zero. There is always a nonlinearity, and that the waves interact. When we had before these distorted plane waves or the plane waves, then they don't interact, they pass through. Because it's a linear equation, the superposition of solutions is a solution. However, for nonlinear equation, there is interaction. We want to use that interaction to create new waves that give information about the inverse problem. So this has been a general topic that has been applied to many different types of nonlinear equations. But let me start first with the case of passive measurements. Passive measurement means it's information that you get. You don't have sources. So you receive light coming from perhaps billions of years ago that you observe now, although light travels very fast, not fast enough in cosmological scale. It takes billions of years for some of the light to come to the Earth to be seen. And since 2015, we have also can observe gravitational waves. So this is a different kind of waves. The problem with this type of receiving light is there is something called gravitational lensing, which we have seen also for when geodesics come together in caustics. So light travels light will curve if there is a large mass. That's the general theory of relativity. The curvature, the gravitational is just the curvature of space-time. So space-time curves and the large mass, and then light is deflected. And then geodesics, which is where the light is propagating. But these are geodesics not for Riemannian metrics, but for Lorentzian metrics that we are going to see in a minute. They get deflected, and you can get many different effects. For instance, this is called the Einstein cross, which has been observed when you have a star and you get 4 images of the same star. Another effect that was predicted by Einstein, in fact, and then has been observed is the double Einstein ring. The double Einstein ring means you have 2 rings of light separated by a darker ring. And this happens when the observer, the star that you want to observe, and the large mass are aligned. They are in the same line. So light doesn't know where to go and goes all around. This is very similar to what happens in optics in some crystals called biaxial crystals. You shoot a ray of light in the direction of an optic axis of a crystal, it splits. And you can see in practice, actually this has been observed, in aragonite, for instance, one of the crystals where this happens, you can see 2 rings of light separated by a darker ring. Very similar to the double Einstein ring. So this is the difficulty that you observe light that may have been deflected by a star. It's not a straight line, otherwise it would be a very easy problem. So, and since 2015, as I mentioned, we can also observe gravitational wave. This is like earthquakes of the universe. The 2 black holes came together and produced a huge gravitational wave that was observed. It's very tiny observation. It's very difficult to observe. It took a long time. And since then, several gravitational waves have been observed. So how to model this observation of light first? So you observe light, so you have a region of space-time that we want to find the structure. Particularly, we want to find the metric. The metric decides the curvature of space-time and the properties of space-time. And in blue here is the region of observation. So we have these point sources of light. So this is the fronts of light. And what we're going to do is intersected somehow this doesn't work. Huh? Slowly, okay. Yes, thank you. And you can do this for different points. So you take another point. Oops. No, even slowly, that's not. Maybe I should go back. Well, anyway, there are the fronts of light come in, and you intersect it with the region of observation. There is a point here, also, and so on. And we're going to assume that you have a dense set of point lights here in this region, and we want to find the structure of this that may be very far in the past. Yeah. Oh, there it is. No, just one. Okay, well, anyway, you get the idea. And so I'm going to make a brief review of Lorentzian geometry. Tomorrow you will hear more. But for the people who are not familiar with Lorentzian geometry, just think of, this is called the Minkowski metric. A metric is a matrix, and this has just, in the time variable, has a negative sign. This is the different than the Riemannian metric. Negative, positive, 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 say in dimension 4. 4 space-time dimension. It's -1, 1, 1, 1. Okay, so this metric is not positive definite anymore. So this is called the Minkowski metric. And then associated to the Minkowski metric, there is the light cone. These are the vectors that for which the metric vanishes. For the Riemannian metric, this never vanishes. This is positive definite. This is the light cone. For instance, these are the vectors where dt squared is equal to dx squared. Right? So think about the light cone. This is the propagation of light. The propagation of light is along this light cone here. This is a forward light cone, and this is the backward light cone. And then in the interior of the light cone is where we are. We are traveling somewhere around here in a space-time. Of course, unfortunately for us, time is limited. We'll end at some point. Nobody has proven that, but and as now it's working. See from the other point, you can see. You look at the intersection. Okay, and then so this is the future light cone and the past light cone. These are, and outside the light cone, you cannot travel because you will go faster than the speed of light, as Sebastian was mentioning this morning. Okay, so Lorentzian just means the signature is minus plus 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 for this matrix. In the Riemannian case, is plus 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 plus. And there is a time, which is, we assume that there is a time. And locally, you have this Lorentzian manifold. It looks like Minkowski metric. Okay. So think about the Minkowski metric if you're not familiar. And then you look at the null geodesics. It's defined exactly the same way as we had before. But now you have a negative, you have not a positive definite matrix like here. And so these are the geodesics. In the case of the Minkowski metric, they are a straight line. And so this is very, what I mentioned before. This is the light cone. Again, think about this metric, the Minkowski metric. The vectors inside the cone are called time-like, because that's where we are going. And space-like is you are outside the light cone. And in the light cone itself, this is the light cone itself. Okay. And then there is something called the chronological future and past of a point. The chronological future means you take the point here, say P, you take the light cone associated to it, which is this big thing here, including the interior where we are traveling. And this is the backward light cone, the solid backward light cone where we are traveling. And in the past, you're going in the past here in the future. And you look at the intersection of the two. So this is the region which will be important. This diamond figure is very important. It's called the causal diamond. So this curve here is an observer, the timeline of an observer. Here we are. We're here. This diamond means the following. If you send waves starting here where we are, then they will come back so you can observe them. This is why it's called causal. So beyond that, you cannot see, you will not be able to see anything. The wave will just go away. So this is an important region, this diamond region here. And this intersection is also important. Any questions? Again, this cone in general can be very complicated, this diamond figure. I'm drawing it here for the case of the Minkowski metric, where this is straight. Okay, and then there is an assumption which is called globally hyperbolic, which is, some people don't believe in this, that there are no closed causal paths, meaning if you go to the future, you cannot come back to the past. Some people believe that you can do both. It's different models of cosmology. And the assumption also is that this set that I was drawing before, JPQ here, this set is compact. Okay, so this intersection of these two things, so this figure is like this, not infinite.
The light speed is finite.
It's finite, right. Exactly. Yeah, no closed core path, any path. I mean, you can, path in the sense of propagation of light. I mean, also you cannot go to the future and come back to the past. That's what it means. More general curves, yeah. And from the analytic point of view, the condition of globally hyperbolic means that the metric is very close to what the Minkowski metric is. There is just a factor here, and I should have said that this is non-zero, positive. It's positive, so before it has just -1. And here, for every t, this is positive definite Riemannian matrix. So I will call y the space variable, and ty, we call it x. So x is ty, which has we're going to just consider 3 space dimension and 1 time variable. You can consider higher, but this is the physical case of space-time. I'm going to assume it's globally hyperbolic. No, this is a consequence. The reason why is this important, because you can show that the hyperbolic equations associated to, for instance, Einstein's equation are well posed under the assumption of global hyperbolicity. Okay, and I'm trying to define what is this picture that we had from before, point sources of light, and we intersect it with the region of observation. So mu is a time-like geodesic, meaning you are inside the light cone. And you take, this is where we are traveling, is the world line of an observer is called in general relativity. And then you take a neighborhood of that curve. Let's imagine it's a straight line. You take a neighborhood. You can take as much time as we have. Hopefully, new generations will continue to make observations. It doesn't end with us, right? And then this is the region W. The region W is the region that we want to determine the metrics, the topology and differential structure and so on. Okay? So then may be very far in the past. So this is the backward light cone, and this is the backward light cone of this point P plus, and this P minus is inside here. And it's assumed to be relatively compact. And you take a point Q in W, and you take the light cone associated to this point Q. So this is where photons propagate, light propagates along the light cone, the boundary of this cone. But you have many directions. So we take the light cone, and we intersect it with the region of observation. So this is what this is. These are geodesics. Geodesics are the propagation of light is along geodesics. Null geodesics, in fact, like I defined before. The Hamiltonian is a little bit different because it's negative, has a negative sign in the time variable. When you intersect it, and this is what we were doing before. I intersect the light cone with this. This is the observation of point sets, points of light that might be very far in the past, billions of years ago. We want to find out what was the structure of the universe in the past. That's the objective. And then we look at, so this is called the light observation set, because these are the observations of light in the neighborhood that we are considering. Yes? Sorry? No. W is the region that we want to observe, right? It's contained here. This regional observation, as it says here, is contained in I minus of P plus, meaning the backward light cone, including the solid part, the whole solid cone here, because that's where we're traveling, and the forward intersected with the backward light cone starting on P minus. Yeah. So it's here, exactly as in the picture. Okay. And then you look at something called the earliest light observation set of the point Q, because this, here I have drawn it straight, like that's the case of the Minkowski metric, and because of gravitational lensing, as I mentioned before, this cone can be very complicated. For instance, come back. You can come back, you can be trapped, many things can happen with gravitational lensing. So we consider the first time that this cone of light intersects this set V. That's called the earliest light observation set. Okay, and now let me point out one thing, that the light cone, this cone, which is the outside, does not change if you multiply the metric by a function, a positive function. You multiply this, what's called a conformal factor, alpha g. The points where 0 does not change because it's different, it's the same. So the light cone is called invariant under conformal changes. It's the same light cone. You multiply the metric by a factor, you get exactly the same. Right? So you cannot recover the metric completely from just looking at the light cones. You can determine the metric only up to conformal factor, up to a multiple. Please stop me if, just think of the Minkowski space. I mean, you don't need to, the ideas are already there. So this is called the earliest observation set, the first time that the light cone intersects the set V. In the Minkowski case, the light cone doesn't come back. So the theorem, you take open, smooth, globally hyperbolic Lorentzian manifold of dimension bigger or equal than 3. And you take 2 points that we had before, 2 points P minus and P plus in the manifold. And then you have, it's called a time-like geodesic. That's the world line of an observer like us. You take these 2 points. You take a neighborhood of this path, this time-like geodesic. Time-like means it's inside the light cone. And you take a set W that we don't know, but is relatively compact. So assume that we know this set, the earliest light observation set. Then we can determine everything about the W, the topological structure, meaning the topology, the differential structure, the differentiable structure, and the conformal, not the whole metric, but the conformal class of the metric, up to change of variables. You always have all of these things are invariantly defined. So there is always the change of variables that is present, as in the anisotropic case. Right? We have a metric here for the Calderon problem. There is a diffeomorphism invariance. Also, in this case, there is a diffeomorphism invariance. When you have things that are defined invariantly, this always occurs, up to change of variables. Yeah. No, not the diamond region. There is no diamond region here yet. This is just a neighborhood, this neighborhood of the Earth, for instance. Epsilon VW is in the intersection. You take a point Q in W, you take the light cone associated to that, and you intersect it with the region B. Intersect with the blue region. That's the neighborhood V of this curve where we are. And then you take every Q in W, you do the same, the intersection with that. The union of all of that. Questions? Is that clear? Huh? Well, Ishao will give you the proof tomorrow, right? And this actually, I gave a talk about this in Santa Barbara, and there was somebody at the end of my talk was this guy, this person Horowitz. He's a physicist. He told me they have also considered this for completely different reasons, and they call it light cone cuts. They were not thinking about the inverse problem. They were thinking about ADS, CFT correspondence. This is something in physics. A very nice name, actually, light cone cuts, because that's what you're doing. You're cutting this neighborhood with these cones. It's a very good name. Physicists are better than us for giving names, fancy names. Okay, so the reason why I want to look at this, because the new waves that we're going to generate will give rise to this light observation set. It's not just I'm trying to be fancy here with all of these Lorentzian geometries. It's because it does show up. Okay. So Yoshua will talk more about this tomorrow. Questions? Okay, so I already mentioned this before. For linear hyperbolic equations, this is a Gelfand problem. And the important thing that I want to mention is that the approach, which is called the boundary control approach, which is based in the unique continuation theorem of Tataru, you need the metric to be independent of time or real analytic in time. And certainly does not satisfy in space-time. There are many phenomena happening in space-time, for instance, black holes. So this is what I already described, so I'm not going to. This is the linear case. We describe it in some detail. So let me go now to the nonlinear waves. So the cartoon is the following. So you have here the Earth across time. This is a cartoon, of course. This is R3, this is cross time. Suppose we are going to make observations near the Earth. So we are going to send 4 waves that will intersect at a point. So these waves, these curves that I'm drawing are the perpendicular to the waves. So we're going to send distorted plane waves, like we had before for the linear equation. The difference with the linear equation that these waves will just continue. But here, because of the nonlinearity, the wave will come back. And we're going to observe it in this cylinder near the Earth. So that's the idea. It's very simple. Right? So because of the interaction of waves, in the nonlinear case, you generate new waves that will determine the earliest light observation set. And from that, you can recover the metric up to conformal factor. There is still this factor that we need to determine as well. Okay, so let me explain this for a simpler model. This is a toy model. It's not a physical example. It's just to explain this in the simplest, perhaps, possible nonlinearity. So you take u of x. Remember, x consists of time and space. X is ty. And this is the wave equation associated to a metric depending on t. You can think about the Minkowski metric if you want, but the theorem is more, because the main point actually what I want to do because of relativity is to recover the metric. That's what I want. Recover the metric of space-time, because that tells you how space-time curves and tells you what happened in the past. How do we know? So you have a source here, F, and this is well posed, so the support is contained in the solid cone starting with the support of F. This is a well posed problem. So the support is contained in this neighborhood where we are. It's an open set. And this is the wave equation. For the Minkowski metric, this is just a standard wave equation. Look, it's very similar to what we were considering before, except for this metric now is minus plus plus plus. So that's why we had to put this negative sign here to make it positive and take the square root. And also here. So this is a more general wave equation with coefficients depends on time. So it's a time-dependent equation. And the source is also time-dependent, because that's what we want, time-dependent equations. Right? Okay, so think of this as a wave equation. So this is the determinant. And this is F is supported. This is we will need the 6 derivatives for technical reasons in the neighborhood where we're making the measurements. We're making the measurements is a neighborhood of a world line of an observer where we are observing. The V is a neighborhood, is this neighborhood here. Okay. And we consider what is called the source-to-solution map. Later on, we are going to consider the Dirichlet to Neumann map. So you send the source. This is the right-hand side of the equation. That's why it's called active measurements. You're sending a source to the solution, which is supported on V, in this neighborhood of the where we're observing, to the solution of V. So what comes back? Right? You have a solution of the wave equation everywhere. Here, this is for any t cross the space variable. And so it's a cylinder. And then we wait for the wave to come back and we observe that. So that's the source to solution. It's called the source to solution map. This is the source, F is the source. Use the solution, and we are only measuring what comes back to the neighborhood where we are observing. Yes? Because of the nonlinearity, they will come back. That's the point. The whole point of this lecture is that because of the nonlinearity, they come back. So we will have interaction. And here, you see, you can send a lot of waves. Right? The F is what we control here. We are going to send actually two different types of waves. You will see in a minute. And then something will come back. We had to prove that, of course. Sorry? Yes, many physical models. Einstein's equation, elasticity, nonlinear elasticity. Young will show about that this happens in nonlinear acoustics. I would say all nonlinear equations. Right, that is, you send waves. Einstein's equation is highly nonlinear. And because of for instance, you take U squared, like in this case. Then they interact, right? And in Einstein's equation, I will show it later, not today, but later, the singularities are much more complicated than that. You have gradients, nonlinearity, square of the gradient, many types of different nonlinearities. Applies to essentially any, this is of course meta theorem, to any interesting nonlinear equation. I'm taking this example because it's easier to do the calculations. You have very simple nonlinearity, quadratic nonlinearity.
To fit this is that good, which nonlinear model to use for our universe, the light property?
It's Einstein's equation.
Then what is the nonlinear?
Okay, so let me tell you. I'm jumping a lot. So this is Einstein's equation coupled with scalar fields. Einstein's Maxwell equation, you couple it with the electromagnetic field. Nonlinear elasticity, Young-Mills. Well, this is a semi-linear equation, nonlinear acoustic. This is what Young is going to explain. So if you want, I can tell you what Einstein's equation is, but there's no point at this point. This is Einstein's equation. This is the Einstein tensor. This is the stress energy tensor. The Einstein tensor is given in geometric terms. That's why we're trying to recover the metric. And you can write the Einstein's equation as a quasi-linear hyperbolic system. Look at the equations here. This depends on the derivatives and the metric itself. And there is, moreover, like Maxwell equations, there is a divergence equation that you need to complicate things quite a lot. So I'm not going to start with Einstein's equation because the computations are very complicated, although we, meaning the three authors, we started with Einstein's equation, but we should have started with a simpler. Took us many years to do Einstein's equation. Okay. So this is a toy model, but explains all the ideas. The ideas for all the other cases are the same. The computations are more complicated, but the ideas are already, you can see them already in this example. Okay, so the theorem in this case, so I'm interested in the metric. You can also show that if you know the metric, you can recover A, the coefficient of the nonlinearity, but my main interest is the metric. So you have, again, a globally hyperbolic Lorentzian manifold. You have a time-like path, that's the world line of an observer containing these 2 points. You take a neighborhood, and A is non-vanishing, that's key. We have always a nonlinearity. If you have A is 0, then we don't know what to do. We don't know how to solve the problem. So the nonlinearity helps, because in that case, the waves just don't come back.
It means also A has a certain sign.
Sorry?
A is smooth and non-zero.
Non-zero, everywhere.
So positive.
Positive, you have to have a sign, otherwise it will be 0. Okay, so you take A non-zero. So suppose you know this neighborhood and the metric in this neighborhood V, and you know the source to solution map. Remember, you take data on V, and you look for the solution that comes back to V. That's the source to solution map. Then you can recover the metric, the conformal class of the metric, meaning the metric except for a multiple. We cannot recover the metric because the light cones don't see the multiple. The light cones is when the metric vanishes in the tangent vectors. In this diamond, in this causal region here that I explained before. You can recover the metric here. The longer the time that you observe, the larger this region is. Of course, it's always up to change of coordinates because the problem is invariant. Okay, so the idea to do this is the following. So you take a point in the diamond. We're going to create artificial earthquakes here, point sources. Then, so we're going to send waves starting on V that will intersect at this point Q, and this will generate a source, and then that will then you will propagate along this cone. The light will propagate along this cone and will intersect with this region, and so will determine the earliest light observation set. Right? Remember, the earliest light observation set for every point in this diamond figure, and using the previous result, we can recover the metric except for a factor. That's the point. And then we can also say not only recover, remember before we were looking at singularities. Here also we're looking at the singularities. We're going to look at the singularities, new waves meaning new singularities. And we're going to also determine the strengths of the singularity. Remember, there was the amplitude of the singularity that we have for the linear case. We're going to be able to determine the strengths of those singularities. And that will determine, in many cases, the conformal factor. Okay, so this is the general picture. Questions? At least I hope the idea gets through. Not for Chaim. So how do we do this? So this is, remember we had before geometrical optics, but now we are going to have nonlinear geometrical optics for nonlinear equations. So we're going to, there is a problem with nonlinear equations in general that there may not be global solutions. You know, there is singularities that even you have take very smooth data, the solution may blow up in finite time. Right? For some equations, it doesn't happen. In that case, you have a scattering. You can go for all time. But for some, you do. So you assume a small data, small f in this case, and that will imply that there are solutions of the equation for any finite amount of time. Okay, so we take epsilon W1, epsilon squared, epsilon Q, epsilon 4. We're going to go to order 4, and then this will be of order, this is proven by energy inequalities of order 5. So we are going to neglect this. Okay, so what is the first term? The first term is the linear term. We want to solve this equal to f if we ignore the nonlinearity, so W1 is the inverse of this applied to f, like the Green's kernel of this equation applied to f. This is the first term, corresponds to the linear case. So now it's like a Picard iteration when you solve an ODE. We go to the next term. We have already W1, so we take W1 squared here, and then take the box inverse of minus a times W squared. Right? That's the next term. So this is the double interaction. This is the triple interaction. Next term, and this is the fourth order interaction. This is Q is the inverse of the wave equation. So the thing is, we know this operator Q is the inverse of the wave equation. We know how singularities are propagated by this. We have analyzed it before, remember, along geodesics, right? This was the phase function that we have from before. That's why I covered that before, to explain that for the linear equation, the singularities propagate along geodesics. You have these distorted plane waves. And we know this is something from macrolocal analysis. We know how to compute the singularities of the double interaction. And because A is non-zero, you can compute an equality for the singularities of W2. And then the singularities of W3 and the singularities of W4. So you can see for Einstein's equation there are, I think there were like 1,000 terms or something of that order. That's why you don't want to cover this. Already for the quadratic equation is quite complicated. So we are going to go to fourth order interaction. The reason is because 4 waves intersect at a point in general in 4 space-time dimension, and then from that point we are going to generate a new wave. This is just to say that there is technology to analyze the product of when you take products of these distorted plane waves, how to compute the singularities, how to compute when you take the inverse, how to compute the singularities, and so on. So we have a technology for all of that. Okay, so for instance, in Minkowski space, this is the case, you take this plane wave that we had before, t minus x dot omega. Omega is the direction of the wave. Remember, we had these plane waves coming in. For Minkowski, this is their solution, so the wave equation. I asked yesterday somebody to show this. These are solutions of the wave equation, like delta, but we take something smoother to some power here, like for m equal to 1, for instance, for m equal to 0 is the Heaviside function, m equal to 1 is x plus, and so on. The same as we had before, these plane waves in different directions. This is for Minkowski space, I'm explaining it there. And then you have the double interaction of these plane waves, the triple interaction, which is a line, where you have 3 waves, 3 plane waves, intersect at a line. And then the fourth order interaction, that's why we're taking fourth order, because the intersection is at a point. Okay. And we look at the interaction of two waves. We look at what's called the second order linearization. The first order linearization, unfortunately, does not give anything because if you linearize this problem, you get the wave equation. And we don't know how to solve the inverse problem for that because the metric depends on time. So linearization does not help. So we go to second order linearization, which means you take two sources, F1, F2. Remember, we have freedom to choose the sources. There are two parameters, epsilon1 and epsilon2, and this is the second order linearization, which is Q. This is the wave U1. This is the wave U2 with data F1 and F2 respectively. And this is the Green's kernel of the wave operator. So this is the second order linearization. Unfortunately, from the point of view of singularities, nothing happens. The singularity, this is called the singular support, means where the singularities are in the same two planes that we have from before. K's are the planes. x1 equal to 0, x2. This is t minus x dot omega 1, t minus x dot omega 2. Nothing happens. So from the point of view of singularities, of course, a lot of things happen, but from the point of view of singularities, nothing new happens. So the singular support is contained in the union of the two plane waves. So what's the joke? You know, math is very dry, so if there is a joke, it will be good you share it with everyone. What's the joke? Sorry? Oh, your pen dropped and you laugh because of that? Okay. Yes?
So the K's either are the singular set
Of U1 and the other one of U2. K1 and K2 are this t minus x dot omega 1 equal to 0. K2 is, so there are two plane waves. There are two plane waves. You send two plane waves. This is the Minkowski's case, right? If you have a metric in general, it will be a distorted plane wave. So you have two waves, and then nothing happens, so you don't see any new singularity. So this doesn't give the second order linearization in this case. I mean, for other equations, does give information because we are trying to recover the metric. For three waves, then there are new singularities coming up. So you have here three plane waves. They intersect in a line, and there is a new singularity coming out. But unfortunately, this singularity escapes. Part of it comes back, a lot of it escapes, and we cannot use it to solve the inverse problem. But one might, but we haven't been able to do that part. And then for four interaction, this is I put it small because they are small waves. So we have four plane waves coming together. And they intersect at a point. And then these rings are the third order interaction. And this is the new wave coming back. A new spherical wave, in the Minkowski's case, come out, and you intersect it with the region of observation, and that gives you the light observation set. And that's the whole point of this. So these rings that you see here, these black rings, correspond to the third order interaction. And this ball that covers everything, it goes everywhere. This is the fourth order interaction. Sorry? Three waves interacting. It's third order linearization. You take three data, F1, F2, F3. The solutions are U1, U2, U3. Remember, we control the sources. We look at the solutions of the wave equation with those sources, call it U1, U2, U3. Right?
So the black were the singularities of
Sorry?
the black regions were the singularities of the
It corresponds to the intersection of the three waves. When there are four waves coming in, it also happens the three of them intersect, right? So that corresponds to these black rings. You have four waves interacting. Three of them are going to interact in a line at some point, and then the four of them interact at a point, right? Intersect at a point, and then generates a new wave. So that's the whole point of this. So this is the fourth order interaction. So the singularities of this new wave are the four planes that you have from before, the continuum. This is the triple order interaction. When three waves interact, they produce these rings you saw, and this is the light cone started at the point Q. This was this part. Sorry. It's four plane waves I want this case. And so this is the main wave that comes up back, and that's what we use because that determines the light observation set, and therefore the conformal class of the metric by the result that we had previously. So these rings here corresponds to the triple interaction. Is there questions about that? And this can be applied to many inverse problems. And let me give you a simpler example. For instance, you take U cubed now plus a source. This is the wave equation. Let's take 2 plus 1 dimension. So the space dimension is 2 and then time. You take, now we take 3 waves. And this, the F1 is this plane wave that we had from before, t minus x, is in the direction x1, plus 11, so it's sufficiently regular. You have to take waves sufficiently regular so you can multiply things, because we're taking cubes here. You have singularities, it's difficult to multiply. And then you simply, the new wave that's generated is the waves that you have from before. And in this case, it's very easy to compute because the amplitude here is 1. So you get just this applied to the product of the 3. And this, when you have the intersection of the 3, you are in 2 plus 1 dimension. Then again, a cone is generated. The light cone started at the point Q. So when you intersect that with the region of observation, you can recover the light observation set. So here you are just doing third order interaction, third order linearization. So linearization is very useful up to a point when you know how to solve the linear problem. Sometimes we don't know how to solve the linear problem, like in this case. You go to second order, doesn't help for this case. But for this particular case, third order, because the singularities of third order. Here, it helps. So Yang will show the case, a physical case in nonlinear acoustic where you just need to have second order linearization. It's much easier to do second order than. Okay, so There has been many cases that this has been tried. So I said Einstein's equation, I will mention this in more detail. I'm running out of time. It's coupled with scalar fields. This is our original paper and was simplified in this paper that was just published. Maxwell, when you couple Einstein's equation with electromagnetic field, Einstein's equation in general, coupled with many different type of fields under some conditions, nonlinear elasticity, many elastic materials are exhibit nonlinearity. Young-Mills equation, this is very important in physics. Inverse scattering for some nonlinear equations. For this, you have to have global existence of solutions to have a scattering. Because you have to go, scattering means you go to infinity in time. Semilinear equations, of course, it's easier and there has been many works, and nonlinear acoustics, you will see it after in the discussion next. Okay, so that's enough for today. People don't clap now, huh? Okay. I'm just kidding. Yes. There is work for when the metric depends on time. No, but it depends what you mean by metric. The metric for some metrics there is work, where it is conformal to the Euclidean metric. There is, for the physical examples, you have to look, it's important to consider physical examples, right? Not just models and others. So for physical examples, for instance, reaction diffusion equations, or porous equation, this has been done. One important case that has not been done, you can try it, is Navier-Stokes, which is a combination of parabolic and hyperbolic. And the problem there is to recover the viscosity. But certainly one should try. And the difficulty there is that waves has a different meaning because in some sense it's parabolic and some sense it's hyperbolic. That's the difficulty of Navier-Stokes. But that will be a very interesting case to consider. Sorry? The metric is not the metric to recover, it's the coefficient. The problem is the system, and second, the behavior, the equation is neither hyperbolic nor parabolic. It's nonlinear, of course. Our interest was to do Einstein's equation because we want to recover very ambitious project to recover the metric of the universe.
How much money do you need for observation?
Well, there are many observations, done. There are many places where there are observations. My native country is very good for astronomical observations. In Chile, there is a spectacular sky, very clear sky. There are many observatories and so on. And the method that they use currently to say, you hear all the time, this is millions of years ago and so on, is ad hoc, right? It's not based on analysis. It's comparing with other data, you compare with what is known and so on, least squares type of things. But nothing, that's based on something more fundamental. This is what we're trying to do so to do something more fundamental. Yes? I cannot hear very well, sorry. For this, for the development? Oh, geometrical optics, okay. This thing? When the leading term, this term? Well, there are, you can try other ways, but this is the way to treat this nonlinearity here. First, it's like a Picard iteration when you solve an ODE, right? You first.
Right-hand side F is epsilon times F1. There is a like F.
Yeah, this is an epsilon F1. The sources are epsilon F1, epsilon F2, epsilon 2, F2, epsilon 3, F3 for the, yeah. Okay. Any other question? Okay.
So no questions, we'll take a coffee break. As you can see there, the posters are already set up outside. Feel free to browse. So then we'll still come back for discussion session first, then the poster session.